So before we start, and after welcoming everybody, I want to introduce Dr. Ahmed Salama, the head of SFTec's technical department. So Dr. Ahmed earned his Bachelor's of Engineering and Master's degree in Structural Engineering from the University of Cairo in Egypt. He worked for the Egyptian Ministry of Water and contributed to several projects during his employment there. Some of the projects are Al Sharika Bridges project and the Ismailia Canal project. He then moved to Quebec, Canada, after being admitted to the Ph.D. program at the University of Sherbrooke to continue his studies in structural engineering under the supervision of Professor Brahim Benmokrane. He basically, during his tenure here, he specialized in concrete structures that are reinforced with fiber reinforced polymers. So if you're interested in this particular subject, he's the right person to learn from. So he joined SFTec in July 2019 as the head of the technical department. He had the opportunity to work with us on several projects in different multiple industries, from telecommunication tower bases, water purification stations, different slab projects, ICF walls, tilt-up walls, and many more. So enough talking, and I guess it's time to listen to the master himself, if you'd like. Dr. Ahmed, the mic is yours.
Thank you so much, Rick, for this great introduction. I highly appreciate it. So again, welcome to all of you from different parts of the world and different time zones. This gives me pleasure to see a really good presence in our webinar. Please stay with us and we all will learn together. Today we are going to talk about design of isolated footing subjected to eccentric loading using fiber reinforced polymer bars. In the next slides, I will go through brief introduction, field application with FRP bars, design of FRP-RC isolated footing, and finally, I will give some concluding remarks based on the presented slides. In the beginning, I would like to introduce our company, SFTec. Who are we? SFTec is a professional entrepreneurial industry in the business of the composite rebar. What do we do and who do we work with? SFTec is working closely with national and international engineering firms and government departments in the construction of parking facilities, water treatment plants, and retaining walls, as well as other structural elements. What is our focus? SFTec is focusing on the market of FRP rebar application in North America and beyond, through providing a complete design for new structures reinforced with FRP bars, and conducting research and development strategies to ensure continuous improvement of SFTec products. The question now, what is the composition of FRP material? As per the microscopic analysis on our right side, we see here that the FRP materials consists of fibers, resin, and the interface between fiber and resin. FRP materials may be bars or sheets. We are using the bars as a creative solution to eliminate corrosion steel problems, while the FRP sheets for strengthening and rehabilitation purposes. In our presentation, we will focus on FRP bars. So now, what are the types of FRP bars? In the market, we have three main types called carbon FRP, armade glass, and recently we have a type called basalt FRP bar. This figure represents the typical stress-strain curve between steel and FRP bars. There is only one difference between steel and FRP, as we see here. FRP bars are linear up to failure without any ductility or yielding point, like versus steel bars. SFTec products. In our company, we are mainly focusing on the production of GFRP materials in terms of straight bars, bent bars, closed loops, and spirals. And also we have a GFRP material called GFRP connectors for sandwich panels. Why you must use GFRP soft bar instead of steel bars? In the last 10 years, FRP bars have been used successfully in hundreds of bridges, parking lots, tanks, and marine structures across Canada and US. FRP materials offer many advantages over the conventional steel bars, like longer service life, improved durability in harsh marine environment, the advantage of corrosion resistance, high tensile strength compared to the yield stress of steel, lighter than steel, no corrosion even in harsh chemical environment, and finally, neutrality to electrical and magnetic disturbance. SFTec products versus existing standards. Our products go through strict testing requirement before they approved for the market as a cost-effective reinforcing materials instead of corrosive steel bars. Our rebar satisfies the minimum requirement of the specification for fiber reinforced polymer code CSA S807 to the year 2019. Also, our rebars meet the minimum requirement of the Ontario Ministry of Transportation classification to be considered for infrastructure works in Ontario province. The FRP testing includes three main categories. The first one is physical properties test, mechanical properties test, and durability test. As an example, I will give you a detailed information on mechanical requirement of the Canadian standard S807 MTO versus safety bar for the mechanical properties of GFRP bars of size number 6. Size number 6 here means 20 millimeter. As we see here in the first row, the tensile strength of safety bar exceeds the minimum requirement of the Canadian standard S807 to the year 2019 and MTO by 60% on average. Also, as we see here on the second row in this table, the elastic modulus of the safety bar exceeds the minimum requirement of the CSA S807 and the MTO by 8% on average. For other mechanical properties, our rebars also exceeded the minimum requirements of the Canadian standard S807 and MTO. Available FRP bars in the market. This table represents the available FRP sizes in the market as per the Canadian standard S807 to the year 2019. As we see here, the available bar sizes ranged from 6 millimeter to 36 millimeter. Sometimes you will hear that GFRP bar number 1. So when you hear GFRP bar number 1, it means you have GFRP bar with 6 millimeter diameter, and so on, as we see here in this red column. Now I will talk about foundations. And generally, we always hear about two different expressions related to foundation engineering, which are footing and foundation. So what is the difference between foundation and footing? Foundation is the lower part of the building structure that transfers the building gravity loads into the earth. Foundations are commonly separated into two categories: shallow foundations and deep foundations. Footing is a foundation that is constructed under the base of a wall or a column. The purpose of footing is to distribute the weight of the building over a large area. The term of footing is generally used in conjunction with shallow foundation, not deep one. Footing is placed directly below the lowest part of the structure it supports. What are the types of footing, or what are the types of shallow foundations? Number one is strip footing. The strip footing is used under reinforced concrete walls to distribute the vertical loads over the soil, as depicted here in this figure. The load is transferred mainly in one direction, perpendicular to the center line of the wall. Number two, isolated footing. Isolated footings are the most common type of foundations in ordinary structures. They are used to distribute column loads on a relatively large area of a soil. As we see here in this photo represents isolated footing. And here the transfer of load will be in two directions versus the strip one. The strip one, the loading will be in one direction only. The third type we have is called the combined footing. If two columns or more are closely spaced, or the required footing sizes overlap each other, the footings are combined in one big footing called combined footing, as we see here on our right side. The fourth type we have here is called strap footing. If one of the footing is very close to the property line, then a stiff beam is used to connect the column to an interior column. And this type called strap footing, as we see here, we have two isolated footing connected with a beam. This beam called strap. And the last type we have is called draft footing. If applied loads are heavy or more than 60% of the isolated footing overlap, a raft foundation is used to support the entire structure, as we see here. This one is similar to an inverted flex slab in which it contains column and filled strips. So now I will talk about the soil pressure under footing subjected to concentric loading. The actual bearing capacity differs significantly according to the type of soil, stiffness of footing, and loading conditions. In general, the distribution under the base of the footing is non-uniform, as we see here in this sketch. This one represents the distribution of the stresses under a footing for a sandy soil. Assuming the loading is concentric and the footing is rigid, the soil pressure under a part is very high, as we see here, like a parabola, and on this part is very low. However, for design purposes, the bearing soil distribution is assumed to be uniform, regardless the type of the soil or the stiffness of the footing, as we see here on our right side. The assumption will simplify the calculation using the actual forces acting on this foundation, and speeds the design process. So we have a footing subjected to a concentrated load called B. What are going to do here in order to calculate the area of this footing? We will equating the actual stress by the allowable stress. The allowable stress here, we can hear another term called bearing capacity. So we will equate the bearing capacity of the soil by the actual stress on the soil. The actual stress here is the B column, the concentrated load we have over the area footing. We have the allowable stress from the soil reports, and we have B column from the analysis. So finally, we can calculate the area of the footing. Now I will talk about soil pressure under footing subjected to eccentric loading. Foundations may be frequently subjected to eccentric loading resulted from lateral loads due to wind or earthquake. As we see here, we have an isolated footing subjected to a concentrated load combined with moment. The moment developed at the base of the footing produce non-uniform distribution. As we see here, we don't have the uniform distribution as we had before with the concentrated loading. We have moments, so the moment and the load will coincide here, and the moment and the load will be subtracted on this side, so we will have non-uniform distribution under the soil. The classical stress equation will be used to determine the distribution of the soil bearing. So here we have area footing called L by B. We have the moment of inertia that will be B by L squared over 12, and the Y equals L over 2. By substituting using these three variables in the classical equation we will get a simple formula that can be used and known for us to calculate the soil pressure under footings. So here, if we have a square footing, B equals L. So finally, we will simplify this equation more and have B over B squared and 6M over B to the power of 3. Now I will shift on the field applications with FRP bars. Really, I would like to highlight on our national and international projects with FRP bars. The first application we have here is the first worldwide waffle slabs reinforced with GFRP straight and bent bars in Araya project. Another application for casting water breaks using our rebars as we see here on our right side. Another example for casting slab on grade in Nova Scotia, Canada, as we see here in this figure on our left side. Finally, we have a great field application with our GFRP shear connectors in precast sandwich panels at one of IBM buildings. Now I will shift to another different applications across Canada. The photo on our left side represents a project with Hydro-Quebec for a precast GFRP concrete chamber. On our right side, we can see another example for the preparation and the installation of retaining RC walls for Il River Il Del House. Another application for reconstructing the deteriorated one-way slabs in the rear parking garage using GFRP bars. The last field application we have today is on flat plate structure of Le Chancelier parking garage in Quebec City. As shown in our right side, the flooring slabs of this two-way parking garage is totally reinforced with GFRP bars. It is worth mentioning that several codes and guidelines are available around the world for design of structural elements reinforced with FRP bars. The design philosophy of FRP-RC isolated footing. So now I will move to the design philosophy for the isolated footing using GFRP bars. I will talk here about the flexural and shear design of such footing. The talk here will be according to the Canadian standard S806 to the year 2012. We have three possible modes of failure of a concrete section reinforced with FRP bars. The first one called balanced failure, which represents simultaneous rupture of FRP bars and concrete crushing. The second one called tension failure, which represents the rupture of FRP bars before concrete crushing. And the last one is the compression failure, which represents concrete crushing while FRP bar remains in the elastic range with a strain level smaller than the ultimate strain. There is only one difference between steel and FRP, which is that FRP are linear up to failure and exhibit no ductility or yielding. Another major difference is that serviceability will be more a design limitation in FRP reinforced members than with steel, due to lower modulus of elasticity, deflection, and crack widths will govern the design. Load factors and load combinations. According to the Canadian standard S806, the code uses the same load factors as in the Canadian standard 23.3 to the year 2014. Load combinations are also the same as in the Canadian standard 23.3 to the year 2014, which are based on the National Building Code of Canada. Material resistance factor. Concrete and steel resistance factor remains the same as in the Canadian standard 23.3 to the year 2014, while FRP resistance factor equals 0.75 for all FRP structures reinforced or pre-stressed. The thickness of the isolated footing is commonly governed by the two-way bunching shear. So the isolated footing should be checked against the two-way bunching shear by comparing the actual shear stress from the acting load on the footing with the allowable bunching shear stress using the available code equations. The check of one-way bunching shear is to be performed, even though it is infrequently critical. In this slide, we have a design example for a square footing supported and 450 millimeter square column. As we see on our right side, the design data are the column loads. We have beaded load, B live load, B wind load, and the alternative moment, M dead load, M live load, and M wind load. We get all these loads from the analysis of the building. We have also here a surcharge equals 5 kilonewton per meter squared due to the live load applied directly to the ground floor. The concrete compressive strength equals 40 MPa and the concrete resistance factor equals 0.65. GFRP SFT bar number 10 is chosen as a flexural reinforcing bar for the footing. The allowable bearing capacity and soil density are 200 kilonewton per meter square and 21 kilonewton per meter cube respectively. In the next slides, we will apply all the mentioned points in the design philosophy of this footing for shear and flexure, in order to have a detailed flexural and shear design for an isolated footing, including serviceability limit state check, as well as one-way and two-way shear check. These following design steps will be performed in the next slides. We are going to have heavy calculations. I'm advising you to have a paper and take some notes. The first step here is to calculate different load combinations in terms of service load and ultimate load. As I mentioned earlier, we have B dead load, B live load, B wind load, and the alternative moment for the dead load, live load, and wind load. What we are going to do now is to calculate the service loads. The service load combination we have is, the first one is dead load, so we will put under the axial load 250 kilonewton and the moment 50 kilonewton. The second service load combination we have dead load plus live load. So we are going to add 850 to 550. So dead load plus live load will be equal 1,400. And M dead load equals 50, M live load equals 0. So finally we will have 50. The last one is dead load, live load, and wind load. By using the same criteria, we will calculate the axial load and the moment. The last load combination we have for service load will govern the design. So we are going to take this one in our calculations. After calculating the service loads, the next step is to calculate the ultimate loads as per the National Building Code of Canada and the Canadian Standard 23.3 to the year 2014. According to these codes, we have 5 loading combinations that may be considered for design of our footing under dead load, live load, wind load. Each load combination should be investigated separately. However, load combination number 3 will govern the design. So we are going to include the load combination due to ultimate loads number 3 in our calculations for the design of flexural and shear. The next step is to calculate the concrete properties. As given, the concrete compressive strength equals 40 MPa. So the elastic modulus according to the Canadian standard equals 4,500 by the square root of the concrete compressive strength. The stress block parameters alpha 1 and beta 1 can be calculated using these two equations as a function in the concrete compressive strength. So alpha 1 and beta 1 equals 0.79 and 0.87 respectively. Step number 3 is to calculate the concrete dimensions in terms of footing area and depth. Let us start with the footing area. The chosen service load combination will be used to calculate the concrete dimensions. So the first thing I'm going to calculate something called the Q net. Q net will be the Q allowable minus the weight of the soil on the footing as well as the surcharge. So Q net will be 200, the Q allowable, minus the weight of the soil, gamma S, by the soil depth, plus the surcharge. So finally Q net will be equal 161.4 kilonewton per meter square. We are going to use the equations I explained before in order to estimate the footing area. We here have a square column. So it is preferable to have a square footing. So what I'm going to use this equation for a square footing. So by substituting for the Q net 161.4 and the loads we have from the service load case, B and M, so we can get B. B here equals 3.14 meter. By approximating the length of the footing B to the nearest 100 millimeters, so we will take B 3.2. The next thing we will go to, we will check the normal stresses under the soil. Now we have the footing area, we have the loads from the service load case. So what we are going to do is to check the maximum and minimum stresses under the footing. The maximum stress under the footing should be less than or equal the net bearing capacity. The minimum stresses under the footing should be greater than 0. Why? Because we don't need to have tension on the soil. And also another check we need to do is to have a Q minimum approximately equal half the Q maximum value in order to avoid any overturning on this footing. So finally here we have a footing area 3.2 by 3.2 for a square column 0.45 by 0.45. So now we will calculate the footing depth. For calculating the footing depth, we will use the load combination from the ultimate loads we get. So we have here ultimate axial load 1829.5. We have ultimate moment equals 112.5. So the next step, we will use these loads in order to calculate the ultimate stresses under the footing. By using the classical equation of stresses, we will calculate ultimate one, the ultimate stress under the footing, because in this side we will combine the moment and the shear. On this side, we will subtract the load from the axial load from the moment. So we will have sigma ultimate one equals 199 kilonewton per meter square, and sigma ultimate two equals 158 kilonewton per meter square. The maximum factored moment. As shown here in our plan, we have two sections to be considered in order to calculate the maximum factored moment on our footing. We have section called II and we have section called II. These two sections are located on the face of the footing. We have here a square footing. So by experience and also by calculations, the two moments here, the moment for section II and section II will be closely the same. So what I'm going to do here, I will calculate the moment from section II, which is a little bit more high than the moment from the section II. So here section I is located at 1.375 meter from the column face. We calculated this by subtracting 3.2 from 0.45 over 2. So here the dimension X equals 1.375. So this area, the shaded one, is called the tributary area. This is the tributary area for the moment. So here we have the stress on this face, but we need to calculate the stress on the other face. Let us call it sigma ultimate 3. Sigma ultimate 3 here will be calculated using triangle similarities. So sigma ultimate 3 will be equal 181 kilonewton per meter square. So now we have the stress on this face and the stress on the other face. In order to deal with this area, we are going to calculate the average stress under this area. So the average stress will be 190 kilonewton per meter square. Again, we calculated before sigma ultimate 3 at the face of the column. We calculated sigma average, which is sigma ultimate 3 plus sigma ultimate 1. So we have sigma ultimate 3, 181, and sigma average 190 kilonewton per meter square. By using the average stress, I can calculate the force on this area. The force here will be sigma average by the area. The area here equals B times X. So finally, we have F equals 863 kilonewton. So I have here the force at the centroid of this area. What I'm going to do now is to calculate the moment. The moment will be simply equal F by X over 2. So finally, we have MF for the section II equals 575 kilonewton per the entire width B. So now we calculated the moment, the maximum factor of the moment on the critical section. What I'm going to do now is to calculate the flexural depth. We are going to use this equation in order to calculate the flexural depth. The flexural depth here equals 670 millimeter. This equation basically is not Canadian standard. Really, as usual, what you are going to do is to assume a reasonable value for the depth, and after that you can check it. But in order to make it easy for you, I'm offering you this equation in order to calculate an approximate value for the flexural depth, which is near to the actual value you should have. This equation is mainly based on a curve called the CG curve, and this curve is related to the European codes. So now we have a flexural depth equals 670 millimeter. So the total depth of the footing will be equal the flexural depth plus concrete cover. We are going to take concrete cover 7 centimeter. So 670 plus 70 will be equal 740 millimeter. We will approximate this value to the nearest 50 millimeter. So we are going to take the total depth of the footing 750 millimeter. So we have the total depth 750 millimeter and the concrete cover 70 millimeter. Finally, the depth will be equal 680 millimeter after this approximation process. In this step, I'm going to calculate the footing flexural reinforcement. Let us start by the spacing between the reinforcing bars. According to the Canadian standard S806 to the year 2012, S maximum should be the minimum of 3 times the footing depth or 300 millimeter. So now we will choose the minimum of them, that will be 300 millimeter. What I'm telling you now is to use 80% from this maximum spacing in order to have a good results and save crack widths and save deflections. You can start with the 300 millimeter, but you are going to try another spacing which will be less than 300 millimeter. We agreed to use bar number 10 of SFTec. So what we are going to do, we will put a single layer of number 10 every 240 millimeter in each direction. So we can calculate the total amount of flexural reinforcement we are going to use using this equation. By using this equation, we will need 14 number 10 bear the entire width of the footing. We have the flexural reinforcement amount, we have the depth of the footing, we have the width of the footing, so finally we can calculate the flexural reinforcement ratio. Using this equation to calculate the balanced flexural reinforcement ratio of the designed footing. So by comparing the flexural reinforcement ratio with the balanced one with the actual one, we will have a compression controlled section. The compression controlled section is the desirable mode of failure, which is preferred by the Canadian standard S806. And after calculating the flexural depth, we need to check the bunching shear capacity of the footing. In order to do so, we need to calculate calculate some properties for the critical section. The critical section, as we see here on our right side, is located at d/2 from each face of the column. So the critical shear section dimensions will be B1 and B2. B1 equals C plus D, and B2 equals also C plus D. So B1 equals B2, and finally we have 1130 millimeter. The bunching shear perimeter will be the summation of these four sides. So we have 2B1 and we have 2B2. So finally we have B node at 0.5D will be equal 4,520 millimeter. Now we need to find the tributary area. That is like the force that pushing down, and it is going to separate the critical shear area around the column from the rest of the footing. We have to subtract the bunching shear area by the footing area in order to get the tributary area. So the shaded area we have here is called the tributary area. How we are going to calculate it? We are going to subtract the area of the footing minus the bunching shear area. So finally we have area tributary equals 8.96 meter square. Using the same criteria, we can calculate the moment of inertia for the tributary area, which will be equal 8.6 millimeter to the power of 4. The effective polar moment of inertia. The effective polar moment of inertia can be calculated using this equation, which is mainly based on the critical shear area dimension and the footing depth. So finally, the effective polar moment of inertia equals 7.13 by 10 to the power of 11 millimeter to the power of 4. So now we need to calculate the ultimate bunching shear force and the ultimate moment acting on this footing at the face of the bunching shear area. Since none of the load combinations we have generates uplift, it can be concluded that the shear on the boundary of the concrete of the bunching shear area is proportional to the tributary area. So V will be equal B ultimate times the tributary area to the area of the footing. So V ultimate will be equal 1,601. Moment on the boundary of the critical section is proportional to the ratio of the moment of inertia to the total area. So we have here M ultimate equals 111 kilonewton meter. The portion of this moment is transferred by eccentricity of shear. So we need to calculate the fraction of moment transferred by shear. This one is called gamma V. Gamma V can be calculated using this equation. So we are going to consider only 0.4 from the ultimate moment to be transferred by shear. The ultimate bunching shear stress due to moment and axial load can be calculated using the eccentric shear model as per the Canadian standard 23.3 to the year 2014. So finally we will have VF equals 0.56 MBA. The ultimate factored shear stress is known for us. The next step is to compare it with the allowable bunching shear stress to check is it safe or not. The bunching shear strength will be the least value from these three equations. In these equations, we have new terms that should be determined. Alpha S. Alpha S based on the column location. We have here interior column, so alpha S will be equal 4. Beta C, which is the ratio between the longer to the shorter sides of the column is equal 1. The elastic modulus of the used bar equals 65 MPa. The flexural reinforcement ratio equals 0.53%. The factor lambda is based on the concrete type. We have here normal concrete type, so lambda will be equal 1. The concrete resistance factor equal 0.65. The concrete compressive strength equals 40 MPa. And the calculated depth of the footing equals 680 millimeters. Using these numerical values in this equation, we will have 3 different values for the allowable bunching shear stress, ranging between 0.87 to 1.81 MPa. We are going to select the minimum value, which is 0.87 MPa. By comparing the allowable stress with the actual stress we calculated, so our footing is safe and no need for transverse shear reinforcement. So now I'm going to check this footing for one-way shear. The critical shear section for one-way shear is located at distance called dV. dV, according to the Canadian standard S806 to the year 2012, equals the maximum of 0.9D and 0.72 T. So 0.9D equals 0.9 by 680, or 0.72 T, 0.72 by 750. So we are going to select the maximum value. The maximum value here equals 612. So the critical shear section is located at 612 millimeter from the column face. So we have here this area, which is the tributary area for one-way shear. So what we are going to do now is to calculate the moment and the shear on the face of the critical shear section. In order to do so, we will calculate the stress at the face of the tributary area, and we have the stress on the other side. After that, we are going to get the average stress under this area, the shaded one. So let us do it. So here, the area for one-way shear equals B times WT. 763 here is the width of the tributary area, WT, and B is the footing length. So here, AT equals 2.44 meter square. As I told you before, we are going to calculate the stress at the face of the critical shear section. So sigma ultimate 4 here equals 189 kilonewton per meter square. After that, we are going to calculate the average stresses here, which will be equal 194 kilonewton per meter square. So now, by multiplying the average stress we have here with the tributary area for one-way shear, we will get the ultimate shear force at the face of the critical shear section, which will be 473 kilonewton. So the moment here will be equal the shearing force we have by WT over 2. So the moment for one-way shear will be equal 181 kilonewton meter. The one-way shear strength can be calculated using this equation according to the Canadian standard S806. In this equation, we have some important factors affecting the one-way shear. The first term called Km. Km is a coefficient taking into account the effect of moment at section on shear strength. Kr is a coefficient taking into account the effect of reinforcement rigidity on its shear strength. And finally, we have Ks. which is taking into account the effect of member size on each shear strength. Finally, one-way shear strength equals 1,149 kilonewton. By comparing both allowable and the ultimate one-way shear strength, our design is safe. So this footing is safe for one-way shear. In step number 7, we will calculate the footing flexural moment capacity as per the Canadian standard S806 to the year 2012, using this equation. All variables in these equations are known or calculated before, except the neutral axis depths. So here we have alpha 1, beta 1, gamma C, phi C, FC, B, and the flexural depths. So the unknown variable for us now is the neutral axis depths. From equilibrium, we can get the neutral axis depths by equating the compression force with the tension 1. So the neutral axis depth equals 136.4 millimeter. Before going to calculate the flexural moment capacity, we need to check the neutral axis depths to the flexural depths of the footing. The neutral axis depth to the flexural depths of the footing shall be greater than this term. So by dividing 136.4 over 680, it will be equal 0.2. So this term greater than 7 over 7 plus 2000 by the ultimate strain in the used bar. Okay. So now we can calculate the flexural moment capacity of the designed footing. The flexural moment capacity of the designed footing equals 4,728 kilonewton meter. By comparing the footing flexural moment capacity and the maximum factor moment, the footing flexural moment is greater than the maximum factored moment. The footing cracking moment can be calculated using this equation. By comparing the footing cracking moment capacity and the footing flexural moment capacity, the footing moment capacity exceeds 1.5 the footing cracking moment capacity. Now we will shift to the serviceability limit state check. As we agreed, in order to have a successful design for any structural member with FRP bars, we should check the serviceability limit state because the design is mainly controlled by crack widths and deflection. In order to do so, we have two checks. The first one is the stress and strain limitation. Let us go with this one. The ultimate stress in the used bar under service load should be calculated using this equation. The Canadian standard S806 allowed using 25% of the ultimate strength of the used FRP bar. So the maximum stress in the FRP bars under full service load should be less than or equal 0.25 from the ultimate strength of the used bar. First, we should calculate the maximum moment in the footing under service load in order to calculate the stress in the used bar at service load level. The maximum moment in the footing due to service load will be calculated using the same criteria as we did with the maximum factored moment. So the first thing we are going to do is to calculate the stress at the face at the critical shear section, and we agreed that the critical shear section is at the face of the footing. So the stress here will be equal 131 kilonewton per meter square. And now we are going to calculate the average stress under this area. The average stress equals 146 kilonewton per meter square. So now we can calculate the force at the center of this area. The force equals 642.4 kilonewton. Finally, the moment under surface load will be equal 442 kilonewton meter per the entire length of the footing. So now we calculated MS and we have the depth of the foundation. So the unknown for us is a factor called K. K can be calculated using this equation, which depends mainly on the flexural reinforcement ratio and the modular ratio, NF. The modular ratio is the ratio between the elastic modulus of the used bar to the elastic modulus of the concrete. So rho F by NF will be 0.012. So finally K equals 0.14. And the stress under full service loads is 60 MPa. By comparing 60 MPa with 25% of the ultimate strength in our bar, so we will have a safe design. The stress in the bar now under service load is known for us. The elastic modulus is known from the design data. So now we can calculate the ultimate strain under full service load. The ultimate strain under full service load equals 0.00092. This one is less than 0.0015. So no need to check the crack width parameter. The crack width parameter is the second check that we need to do for the serviceability limit state according to the Canadian standard S806. Finally, we have here the reinforcement details for the isolated footing we design. As per our design, we will use 14 number 10 in both directions. Based on the presented slides, I'm going to give these concluding remarks. Number one, SFTec bar is a very good solution to reinforce concrete infrastructures located in harsh environments. FRP rebars have been used successfully in hundreds of bridges, parking garages, pavement piles, foundations, and other structures across Canada and US. The stresses under the isolated footing should be compression stresses in order to avoid overturning of the footing. The isolated footing must comply with the flexural and shear provisions according to the Canadian standard S806-12. Due to the lower modulus of elasticity of FRP bars, deflection and the crack widths will govern the design of such footing. The thickness of the isolated footing is commonly governed by two-way bunching shear check. Thank you for your attention with me.